Car stopping. Here we have a car which will travel in this direction and a child on a scooter travelling in this direction. At this point here, the driver saw the child, and it took them till this point here before they had managed to apply the brakes. And here is where the car stops. The distance from seeing the child to applying the brakes is called the thinking distance. The distance from applying the brakes to stopping is called the braking distance. And the total distance, including the thinking distance and the braking distance, is this, and that is known as the stopping distance. So the thinking distance is the distance the vehicle travels during the driver's reaction time. The braking distance is the distance the vehicle travels while braking. The stopping distance is the thinking distance plus the braking distance. Just to stress, the thinking distance is the distance the vehicle travels during the reaction time. There is a tendency for people to put that the thinking distance is the time taken for the driver to respond. That is their reaction time. Now to look at some of the factors that affect thinking distance or braking distance. Tiredness. Well, when you're tired, you may react more slowly and so travel a little bit further before you apply the brakes. When you apply the brakes, you're likely to press them just as hard as when you're not tired. So tiredness would affect thinking distance. Ice and rain would reduce the amount of friction between the tyres and the road. It wouldn't affect your reaction times, and so ice and rain would affect braking distance. Drugs would slow down your reactions and so affect your thinking distance. The condition of the tyres and brakes would affect how quickly you could brake, but not how quickly you responded, and so that would affect the braking distance. Alcohol, being a drug, would slow down your reactions and affect your thinking distance. Just to stress, if asked for two different factors, don't put drugs and alcohol as your two different factors. The number of passengers in the car will increase the mass of the car, and so for the same braking force would reduce your deceleration and so increase your thinking distance. So the number of passengers would affect the braking distance. The speed of the car, well, the faster you're travelling, the further you're going to travel while reacting, and the longer it will take you to stop. And so speed affects both thinking distance and braking distance. Look at the thinking distance and braking distance for a range of speeds. At 20 miles per hour, which is 32 kilometers per hour, the thinking distance is 6 meters, the braking distance 6 meters, giving a stopping distance of 12 meters. At 30 miles per hour, or 48 kilometers per hour, the thinking distance is increased to 9 meters, the braking distance to 14 meters, giving a stopping distance of 23 meters. 40 miles per hour, we get a thinking distance of 12 meters, braking distance of 24 meters, and a stopping distance of 36 meters. So you see, in doubling the speed from 20 miles per hour to 40 miles per hour, we double the thinking distance. So thinking distance is directly proportional to speed. However, we've got a fourfold increase in braking distance. We'll look at why this is later. At 50 miles per hour, we have a thinking distance of 15 meters, braking distance 38 meters, stopping distance of 53 meters. 60 miles per hour, thinking distance 18 meters, braking distance 55 meters, stopping distance 73 meters. So again, you see, in going from 30 to 60, we double the thinking distance and have around a fourfold increase in the braking distance. At 70 miles per hour, thinking distance 21 meters, braking distance 75 meters, giving a stopping distance of 96 meters. Let's run through an example. A car of mass 1200 kilograms has brakes that can exert a force of 18 kilonewtons. If the car is travelling at 20 meters per second and the driver can react in 0.7 seconds, calculate for A, the deceleration during braking. Well, we can use the formula A equals F over m, because a deceleration is just a negative acceleration. The force of 18,000 newtons over 1200 kilograms gives a deceleration of 15 meters per second squared. B, the thinking distance. Well, this is before the brakes have been applied, and so the car travels at a constant speed, so we can use the equation distance is equal to speed times time, giving a thinking distance of 40 meters. Part C, the braking distance. Well, for this we can use v squared equals u squared plus 2as. Rearranging for s and putting in the figures gives a braking distance of 13.3 meters. Part D, the stopping distance. Well, that's just the sum of the braking distance and the thinking distance, and so the stopping distance is 27.3 meters. Part E, the braking distance if we double the speed. Well, again using v squared equals u squared plus 2as, rearranged for s, putting in the figures, gives a braking distance of 53.3 meters, which is around 4 times the braking distance at this speed. We can use energy arguments to explain why, as we double the speed, the braking distance should increase by a factor of 4. The kinetic energy of the car while it's moving will be equal to the work done by the brakes in bringing the car to a stop. So, half mass times speed squared is the kinetic energy, will be equal to force applied multiplied by distance moved in the direction of the force for the work done by the brakes. If the speed increases by a factor of 2 to 2v, kinetic energy would then be half mass times 2v squared, which is 2mv squared. So the kinetic energy increases by a factor of 4 if we double the speed. If we can't increase the braking force, the only way to do 4 times the work is to apply the force over 4 times the distance, hence the quadrupling of the braking distance.